This video is about L'Hopital's rule. We're first going to review limits from Calculus AB, and then we're going to talk about what L'Hopital's rule is and apply it to several limit problems. Then we're going to take a look at an exploration dealing with different types of indeterminate forms other than the ones we formally know, and do problems where we manipulate before using L'Hopital's rule. So with that said, we're going to start with this exploration that you see here on the screen. And this exploration requires us to use a calculator to complete the table and estimate the limit. So what I'm going to use is Desmos to help me estimate the limit. So what I'm going to do here is pull up Desmos like you see here. And I'm going to type the function in. So it's x squared minus 3x plus 2 over x minus 2. And it draws the graph. Then you're going to click on this edit list cog here. And then you're going to change it to a table. And it generates a table of values for you. What I'm going to do is I'm going to go and delete all of these values and type in the actual values that were in the table. So 1.9, 1.99, 1.999, 2.001, 2.01, and 2.1. So as x gets sufficiently close to 2, we want to see what y arbitrarily gets close to. And you can tell based on these values, our guess, or my guess rather, would probably be 1. So I'm going to go and fill out this table here based on the results I found in the Desmos calculator. So this is 0.9, 0.99, 0.999, and then on the other side, 1.001, 1.01, 1.1. And so my guess is that the limit is 1. So that would be my guess based off the values in the table. Next, for part 2, it says use algebraic manipulation to find the limit. So what I'm going to do first is I'm going to check my numerator and denominator. And what you notice is both numerator and denominator are 0 when you plug in the 2's. So what we're going to do now is factor the numerator. So when I factor the numerator, that's x minus 2 times x minus 1 over x minus 2. And then we're going to cancel out the x minus 2's. So that leaves us with the limit as x approaches 2 of x minus 1, and if you plug in the 2, you get 1. So we got 1 using algebraic manipulation. Part 3 says let f of x equal x squared minus 3x plus 2, and let g of x equal x minus 2. Compute f prime of 2 over g prime of 2. So this is using calculus to determine what this is. So we're going to find f prime, and that's going to be 2x minus 3, and g prime, which is 1, using our derivative rules from AB. Now I'm going to plug in 2, and once you plug in the 2, you get 4 for f prime. I'm sorry, not 4, you're going to get 1 2 times 2 is 4 minus 3 is 1. And g prime, you get 1. So now you take f prime divided by g prime. So f prime of 2 divided by g prime of 2, which is 1 over 1. And that ends up being 1 again. So now we have verified that the limit is indeed 1. And so part 4 says use the results from above to make a conjecture about how to find the limit of x squared minus 3x plus 2 over x minus 2 as x approaches 2. So my conjecture would be the following. Find derivatives of f and g, and then substitute x equals c. So that conjecture leads to the main topic of this video, which is L'Hopital's rule. And so this is L'Hopital's rule right here. And the most important thing in this theorem is the following statements. That first sentence right there, which talks about f and g being differentiable at c on this open interval. Second, if I evaluate limits and I get both numerator and denominator 0 or both numerator and denominator infinite, then what I can do is to use derivatives to help me find the limit. In other words, the limit of f over g as x approaches c equals the limit of f prime over g prime as x approaches c. So this is only a true statement given if we're using L'Hopital's rule. So what you're going to notice in the next few problems is if I have a fraction, then I know I can apply L'Hopital's rule, but in order to do that, I have to use the different conditions of the theorem. So let's take a look at some examples here. So let's take a look at the first one. And so we're going to find this limit by using L'Hopital's rule, for sure. Because first of all, this is divided, and you're taking the limit of two things divided. The first thing we want to do is talk about differentiability. So you need to name your functions f and g. So f is 2x squared plus x minus 6, and g of x is x plus 2 are differentiable, and I'm going to abbreviate, at x equals -2. So the differentiability condition is met, and I'm not just writing it just to write it. I know that is true because if I mentally take derivatives of the numerator and denominator and plug in -2, I know I'm going to get an answer. Next, we're going to find the limit of each piece of the fraction and see what happens. So if you plug in the -2 in here, you get 0. And for the denominator, you plug in 2, you also get 0. So we can use L'Hopital's rule. So the limit as x approaches -2, 2x squared plus x minus 6 over x plus 2 implies limit x approaches -2 of 4x plus 1 over 1. Okay, and now I can plug in the -2, and when I plug it in, I get -7 as the limit. Okay, and I'm going to put in here, I'm just going to put L'Hopital's here, just his name. Actually, I'll write it in a different color so you can see. And I always do this so that way uh, anyone that reads this can understand I actually use L'Hopital's rule. Okay. So the important pieces are talk about differentiability, check to get your indeterminate form, use L'Hopital's rule correctly, and then reevaluate the new limits. Okay, so you need at least these 4 pieces to get credit. All right, here's another one. So I'm really going to be doing a whole lot of writing, not a whole lot of discussion, because the process is the same. So first, I'm going to talk about differentiability because first, again, I notice it's a fraction, so I can assume I can use L'Hopital's rule. So let's discuss differentiability. So I'm naming my functions. So there's a differentiability condition. Next, I'm going to check indeterminate forms. So both of these evaluate to 0. So now I can use L'Hopital's rule. So taking the derivative of our numerator, we get 6x squared plus 10x, and denominator, three x squared plus 2x minus 10. And so now I can evaluate the limits, and when I do that, I get 12 over negative 5. And let me specify, use L'Hopital's rule. Yeah. Now this problem is an unusual problem because it involves a definite integral. And these types of limits you normally find in calculus BC. Okay, but again, the process is still the same. You have a fraction, and so we could use L'Hopital's rule if we wanted to see what happens. So let's talk about differentiability. So that integral is a function of x because there's an x as one of your bounds. I know they're both differentiable at x equals 1. So now I'm going to check indeterminate forms to see what happens. And so that's this numerator is 0 because to evaluate this definite integral, you're going to substitute the 1 in here, and you get the definite integral of 1 to 1 of dt over t, which is 0. Then substituting the 1 in here, you get 0 as well. There's the indeterminate form. So now we can use L'Hopital's rule. And I'm going to talk about this result. And so when you plug in the 1, you get 1. Okay, so first thing is they use L'Hopital's rule. Second of all, let's talk about this derivative. So as a side note, the second fundamental theorem of calculus, or second FTC, recall that it says if I take the derivative of a definite integral from a to x of f of t dt, if I take the derivative of this definite integral, then it's going to be the original function with x plugged in. So this is a very important theorem that you will need to recall from Calculus AB if you want to be able to do these problems. So if you understood these three examples I did, then you should be able to do these, all of these problems. Now you notice these limits over here have infinity in them. So when you, if and when you use L'Hopital's rule on these, you can discuss differentiability at every x. So you need to determine for these two, when you do your analysis on differentiability, if these functions are differentiable everywhere. So now let's take a look at some problems dealing with trigonometric functions. Again, we have a fraction here, so the same process will apply. So first, talk about differentiability. And we know that sine of anything, no matter what it is always going to be differentiable. Now I'm going to check my indeterminate forms. So this is 0 because if I substitute 0 in here, you get 6 times 0, which is 0. And sine of 0 would be 0 because at 0 radians on the unit circle, that is the y, 0 is the y coordinate at 0 radian. And then substituting in your denominator, you get 0. So we can use L'Hopital's rule. So this limit implies the following limit. And so now you're going to plug in your 0 and you get 3/2. So when you plug in 0, you get cosine 0, which is 1, and then times 6 is 6, okay? And then divide that by 4. And again, make sure you use L'Hopital's rule. So if you are noticing in the examples I'm doing here in this video, the process is still the same for most of these, except we're working with different functions. Okay, so here's a limit involving inverse trig. Again, same rules apply. Let's talk about first differentiability. Next, let's evaluate each function to see what the limit will be. So inverse tangent of 0 from inverse trig is 0 because we're 0 radians because we're looking for the angle that has a tangent value at 0. And then here, this is 0 as well. So I can use L'Hopital's rule. So this limit implies and now we're going to plug in the 0 and we get 1 over 1, which is 1. And again, we use L'Hopital's rule. Okay. So here's another limit problem involving a definite integral, involving trigonometry. So again, just like before, check differentiability. After we check differentiability, we evaluate so remember, plugging in 0, the definite integral from a number to itself is always going to be 0. And then plugging in 0 in here, you get e to the 0, which is 1, minus 1 is 0. So there's the indeterminate form. And so now we're going to use L'Hopital's rule. So this limit implies this limit. And now we're going to plug in 0. We get 1 over 1, which is 1. Again, L'Hopital's rule. So again, another set of problems dealing with trig. So if you understand these problems dealing with trigonometry and inverse trig, then you can practice these problems as well. Okay. So up to this point, we have utilized L'Hopital's rule flawlessly with limits dealing with fractions. So now we're going to take a look at this set of problems dealing with other indeterminate forms to see what's going to happen here. So we got these 4 limits here, and we're going to describe the result of each limit using direct substitution, and then we're going to find each limit by generating a table of values. And we're going to estimate these limits using the Desmos calculator. So first thing I want to do is I want to evaluate each of these using direct substitution. So if I substitute in 0, I get 0 for x, so 0, and this is the limit of x natural log x as x approaches 0 from the right. So I get 0 times natural log of 0 is negative infinity. So now the question becomes, what is this exactly? What is this exactly? Well, one person could say that this could equal 0 because 0 times anything is 0. We can also say that this is negative infinity because negative infinity is bigger than 0. But if we can say that it's either one of these or both of these, then mathematically that's not possible because you can't have an expression equal to 2 or more things. So this is why it's indeterminate here. We go over here to the next one. If you plug in your 0, you're going to get 1. And then plug in 0 in here, you're going to get 1 over 0, which is infinity. So just like in the prior limit, is this 1? Based on what we've been taught in math, or is this infinity? Well, again, there's another indeterminate form because we don't know 1 or we don't know if it's infinity. So let's go to the expression down here. If I plug in 0, I get 0 to the power of 0. So I ask the question again. With an expression like this, one can say, well, this is 0 because 0 to any power is still 0, the way we've been taught. Or is this 1 because any number to the 0 power is 1? Again, we have another indeterminate form. And finally, we come to this expression, 1 over x minus square root of x plus 1 over x. Well, if I plug in 0, I get infinity minus infinity because you get a number over 0. Well, and the way we've been taught, well, if I'm subtracting the same thing, could it be 0? Or infinity is a very large number. So which infinity is bigger? Is it this infinity over here? Because if it is, then this expression is infinite. Or maybe this is infinite. And that could be negative infinity. Either way, it could be one of these three and we have another indeterminate form. So we have at least four additional indeterminate forms. Okay? And we'll talk about how to handle these in the next few examples. So now let's estimate the limits. So let's start with x natural log x. So I'm going to use my Desmos calculator. I'm going to go back to my table here. I'm going to delete, let me see, if I highlight the whole function. Yes. So I have x natural log x, and then I'm going to change my values. I'm going to delete them all first, so I can have an empty table, and then I'm going to plug in numbers getting closer to 0 from the right side. Okay, so normally what that looks like is 0.001, then 0.01 and 0.1, and then let's do 0.2, and then let's do 0.5, and then let's do 1. Okay. Now you could have went up by a tenth, however you want, but I just looking at a table of values. So if I start here and make my way back up to the table, which means I'm getting closer and closer to 0, as you can see, my y values for this function they're becoming negative, but really they're becoming closer and closer to 0. And you can tell from this graph, if I travel on this graph all the way back to 0 on the x, it's going to get closer and closer to 0. So my guess for the limit here for x natural log x as x approaches 0 from the right, my guess would probably be 0. I'm going to guess 0. Remember, it's just a guess. At this point, we don't know really what the actual limit is until we do examples. Okay, the next expression is x plus 1 to the power 1 minus x. So I'm going to come back here and delete this, keep my same table of values. And so let's take a look at what's happening to our values. So I'm going to start with 1, and then I'm going to work my way back up. As I get closer and closer back to 0, what's happening to my values is they're getting closer and closer and closer. Looks like the 2.712. So my guess, that would be my guess, 2.712. Okay. So again, I'm emphasizing the fact I am guessing a limit. You guess a limit, you're not going to know if you're correct or not. The 2.717 will be my guess. Now I'm going to take a look at x to the power of x and find out what the limit is as x approaches 0 from the right. So again, as I go back up in my table, go closer and closer and closer to 0, okay? Closer and closer and closer to 0. It looks like my y values are getting closer and closer and closer to about 1. About 1. So I would guess my limit would be approximately 1. And then finally, this last limit here, 1 over x minus square root of x plus 1 over x. I'm going to type that in here. So I'm going to scroll down. Okay, so as I get closer and closer and closer to 0, it looks like my y values are getting closer and closer and closer to negative 0.5. So I would guess that my limit is negative 0.5. So the whole point of this exploration is to discover these new indeterminate forms and talk about how we're going to be able to deal with these indeterminate forms and how does it relate to L'Hopital's rule. So on this page, we have several indeterminate forms. So we already know about the first two, 0 over 0 or infinity over infinity. If we get one of these, we can use L'Hopital's rule directly. However, if we get any of these 5 here, 0 or negative or infinity minus infinity, 0 to the 0, you either have infinity to the 0 or 1 to the infinity, then you cannot use L'Hopital's rule. I repeat, you cannot use L'Hopital's rule. That means you have to algebraically manipulate until you get either 0 over 0 or infinity over infinity, so you can use L'Hopital's rule. So each of these gives a different strategy depending on what indeterminate form you have, okay? So 0 times infinity, you have to keep manipulating until you are able to get a fraction, all right? Infinity minus infinity, this says to factor, to make an indeterminate product. I like to say get a common denominator, because once you get a common denominator, you're more than likely are going to get a fraction. So I'm going to write here, get a common denominator. Or try to get a common denominator. Because it's normally going to be 2 fractions that are going to be subtracted from each other. 0 to the 0, infinity to the 0, or 1 to the infinity. You want to take the natural log of bring in natural log to make an indeterminate product, which brings you back here. So what we're doing is we're trying to make our way back from here to here and eventually get here is our goal, to use L'Hopital's rule. So now let's take a look at some examples. So all of these examples you'll find in Calculus BC. Calculus BC. So let's take a look at this. So we have limit of x cubed cotangent x as x approaches 0 from the right. So what we want to do is first, because it does not look like a fraction, I can't use L'Hopital's rule right away. So I want to do direct substitution. And so direct substitution, I'm going to come up here and write it. So I want to do limit as x approaches 0 from the right of x cubed. Well, that's 0. And limit as x approaches 0 from the right of cotangent x. That's actually going to be infinity. So we got the indeterminate form 0 times infinity. So I'm gonna come over here and write 0 times infinity. Okay, so we cannot use L'Hopital's rule. So now how do we handle a situation like this? Well, you wanna see if you can rewrite this as a fraction somehow. Well, the nice thing about cotangent x, it is a fraction. I prefer you convert it to a tangent. It'll make life easy. So rewriting this, we'll come down here and put equal sign. That's going to be the limit as x approaches 0 from the right side of x cubed over tangent x. Okay, now we have a fraction. So we're ready to check the indeterminate form just to make sure. So numerator is 0, denominator is 0. Okay, so they're both 0. I also need to talk about differentiability. Use L'Hopital's rule. So I know that, let me also state that f and g are differentiable at x equals 0. So now I'm ready to use L'Hopital's rule. So this new limit right here implies the limit x approaches 0, 3x squared over secant squared x. And now I'm ready to plug in my 0, and that's going to give me 0 at the top over 1, which is 0. So the limit is 0. So for this, you want to get credit for the process, you need to show this form here, show some manipulation here. Of course, talk about differentiability because you are trying to use L'Hopital's rule, show your indeterminate form again, and then use L'Hopital's rule correctly. So remember, you can only use L'Hopital's rule when you have 0 over 0, infinity over infinity. Next. So we have limit of 1 plus 1 over x as x approaches 0. I'm sorry, x approaches infinity. All right, so first thing I want to do, even though there's a fraction in here, I still don't want to draw conclusions about L'Hopital's rule. So I want to consider the different pieces here. So what I'm doing is evaluate the limits of the base. So this is going to give me 1, and then the limit as x approaches infinity of x, that's infinity. So that gives me the indeterminate form 1 to the infinity. Okay, so because we have 1 to the infinity, if we recall from our list of strategies from the table, we have to bring in natural log. Okay, so I need to set this equal to y. So what I'm going to do is set this limit. So I'm going to say y equals, limit as x approaches infinity of 1 plus 1 over x to the power of x. Okay, then I'm going to take natural log of both sides. So I'm going to take natural log of y here, and then I'm going to take natural log of y in front of here. And that's going to give me natural log of y equals limits as x goes to infinity. Now what's going to happen is the natural log is going to force the exponent to come in front. So we now have x natural log 1 plus 1 over x. And now we have a new form. And so now I need to check the indeterminate form. So if I do limits, x goes to infinity of natural log 1 plus 1 over x. Well, we knew this was 1 before, but ln of 1 now is 0. And then limit as x goes to infinity of x is infinity. So we got now the indeterminate form 0 times infinity. Okay, so now remember, if we get this, then we have to we have to manipulate this to where it will be a fraction. So what I'm going to do is on the right side of the equation, so I'm gonna put this over 1, but then what I'm gonna do is I'm gonna multiply by 1 over x over 1 over x. So I want to cancel out this x. So if you divide this by x, then you got to divide your denominator by x, which is the same as multiplying by 1 over x and 1 over x. So now I have the following limit. So I have natural log 1 plus 1 over x over 1 over x. So I got another form. Okay, so now what I have to do is check the indeterminate form once again. Every time I get a new form. So we know numerator is 0. And we know that denominator is 0. Okay, so it looks like we got 0 over 0. And we can use L'Hopital's rule, so we need to discuss differentiability. Okay, so we know that this is, so we know that f is natural log 1 plus 1 over x, and g of x is 1 over x, are differentiable for x greater than 0. And the reason why we have to say that, because we're dealing with, first of all, we've got a natural log up in here, so we're assuming that this is, we're dealing with positive values only. So we're good with this condition. So now I'm ready to use L'Hopital's rule on the right side. So when we come down here, so remember I have natural log y equals limits x approaches infinity. Okay, I'm just going to go ahead and take the derivative of this, of the numerator and denominator. So I have 1 over x, negative 1 over x squared, over 1 plus 1 over x, all over negative 1 over x squared. And now I can cancel. This will cancel with this. So now natural log y equals limit x goes to infinity of 1 over 1 plus 1 over x. So when I take the limit, I get natural log of y gives me 1. Because if you plug infinity in here, you get a 1 over 1 plus 0, which is 1. But I don't want natural log y, I want y. So remember from algebra that natural log y is log of y base e, that's equal to 1. And then we rewrite this. So e to the first power equals y, to solve for y. And so we get y equals e to the first power, which is e, which is the limit. So you have to do all of the process just to get E. So there are a lot of different parts to this. Different parts. So of course you get the indeterminate form, then taking natural log both sides. All right, to make sure you bring down the exponent, then rewriting into a fraction. Okay, checking indeterminate forms along the way. Okay, talking about differentiability, using L'Hopital's rule. And then solving for, once you use L'Hopital's rule, solving for y, and you get your answer. So there's a lot of steps in there. All right, here's another one. So again, we want to check the indeterminate form. So we got 3x minus 12, the limit as x approaches 4 from the right, that's 0. And then we got the limit as x approaches 4 from the right of x minus 4, that's also 0. So that implies the indeterminate form 0 to the 0. So now, just like in the previous example, we need to bring in natural log. So let's bring in natural log. Actually, that's not the first step. First step is to set our limit equal to y, and then we bring in natural log. So let's write the limit equation. Now let me bring in ln here and ln over here. So we get natural log y equals limit x approaches 4 from the right of x minus 4 times natural log 3x minus 12. All right, so we take limits again. Okay, so this time we got the ln term, so that's going to affect the different form. So this is 0. I'm sorry, that's not 0. That's going to be negative infinity. And then if I take the limit as x approaches 4 from the right of x minus 4, that's 0. So that implies 0 times negative infinity. Okay, so that means we have to manipulate this. So what I'm going to do is I want to cancel out this x minus 4 term. So what I'm going to do is rewrite this over 1, but then I'm going to multiply by 1 over x minus 4 all over 1 over x minus 4. Okay, that gives me another form, and that new form is natural log y equals limit x approaches 4 of natural log 3x minus 12 over 1 over x minus 4. We got a new form, so we're going to check limits again. So that's going to be negative infinity once more. Okay, and in our denominator, that's going to be infinity. So we got negative infinity over infinity, so I can use L'Hopital's rule. But before I do that, I need to talk about differentiability here. So we know that f, okay, we know that f and G are differentiable at x greater than 4. Okay, so once I say that, then I can use L'Hopital's rule. So let me come over here. I got natural log y. We'll go ahead and take the derivative of this. So the derivative of my numerator is 3 over 3x minus 12. Derivative of my denominator is negative 1 over x minus 4 all squared. So what I can do is simplify this. So there's actually x minus 4 term here that I can cancel out. So that's natural log y. It's going to give me 3. So I'm going to factor out a 3. And then it's going to cancel here. So that's going to leave in the top a 1 over, and I cancel one of these down here, which is x minus 4. And it's still negative. Okay? It's still negative. I'm sorry. That's going to give me 1 over negative 1 over x minus 4. And so when I plug in, and I got to write my limits, so this will give me 1 over negative 1 over x minus 4. So if I plug in 4 here, actually you need to simplify this because if you plug in 4, it's not going to help. Okay. So that was the original fraction. When you simplify that, you're going to get negative x minus 4. And if you plug in the 4, you're going to get natural log y equals 0. But remember, you got to solve for y. So that's log of y base e equals 0. And when you write this in exponential form, you get e to the 0 equals y, which is 1 equals y. So the limit is 1. The limit is 1. So again, a lot of pieces to this. Lots of pieces to this. Indeterminate forms and the rewriting, algebraic manipulation, and using L'Hopital's rule stating these different pieces. There's a lot to this. All right. Here's our final example of L'Hopital's rule. So here, what we want to do first is take corresponding limits. I recommend you don't handle these separately, because if you try to handle them separately, it will not work out well. So let's approach 2 from the right of our first fraction. So that's going to be infinity. And our second fraction, we take the limit. That's going to be infinity as well. So that implies the indeterminate form infinity minus infinity. Now remember, if you get infinity minus infinity, you can do one of two things. You can factor out the x squared minus 4, or you can just combine them as one fraction, because they both have the same denominator, which is what I would recommend you do here. So we have the limit as x approaches 2 of 1 minus square root of x minus 1 over x squared minus 4. We have a new form, so we have to check limits again. you substitute the 2 in here, you're going to get 0. You substitute the 2 in here again, you're going to get 0. So I know I can use L'Hopital's rule, so I need to talk about differentiability of my functions at 2. Now I can use L'Hopital's rule once I've stated that. So I have limit as x approaches 2 from the right of 1 minus square root of x minus 1 over x squared minus 4 implies the limit as x approaches 2 from the right, the derivative of your numerator is going to be negative 1/2 times x minus 1 to the negative 1/2 times 1 over 2x. And you might want to, simplify this a little bit. Wouldn't hurt. So what's going to happen in here is that's going to come to the denominator. The 2 is going to come to the denominator. So what we're going to have here is a negative 1 over 4x times square root of x minus 1. And then I can evaluate the limit. And once I substitute my 2 in here, I'm going to get a limit of negative 1/8. That will be my limit. So again, the indeterminate form, the rewrite, another indeterminate form. Talk about differentiability, use L'Hopital's rule. And then the direct substitution. So we have come to the conclusion of this video on L'Hopital's rule. Thank you so much. And if you have any questions, comments, or concerns, please feel free to reach out to me via email.